Hello, dear learners, and welcome back to the Lesson BCE YouTube channel. Today, we are going to see stars, literally. We'll be diving deep into their properties, classification, formation, and evolution. It's an epic, cosmic scale explainer, today zooming all the way out from astronomical distances down to the fiery lifespans of giant suns. And hey, before we launch into the cosmos, don't forget to subscribe and like our channel. Okay, let's get into it.
So, here's our roadmap for today. We're splitting our journey up a bit. First, we'll measure the universe. Then, we'll classify the stars, watch a star be born, follow the life of a solar mass star, and finally, wrap up with the high mass finale. All right, kicking things off with Section 1, measuring the universe. Seriously, how do we actually know any of this stuff? You know, it's a totally fair, highly skeptical question to ask. How do we possibly know the distance to an object that is literally millions of light years away? We obviously can't just stretch a tape measure across the void. So astronomers use our first major tool, which is called parallax. This is basically the foundational rung on what astronomers call the cosmic distance ladder, and we use it directly for our closest stellar neighbors right here in the Milky Way galaxy. Think of it like this. If you hold your thumb out at arm's length and close one eye, and then switch and close the other, your thumb appears to kind of jump back and forth against the background. That visual shift, that's parallax. Astronomers do the exact same thing with stars, but instead of using two eyes, they observe a star from one side of Earth's orbit around the sun, and then they look again 6 months later from the other side. By measuring that tiny shift against distant background stars, they can calculate the exact distance.
Okay, but eventually, stars are just too far away for that parallax trick to work. So let's step up to the next rung on our distance ladder. That's where standard candles come in. These are celestial objects like pulsating Cepheid variable stars or explosive supernovae whose actual true luminosity is already known. And by luminosity, I mean the total energy emitted by that star every single second. Now, brightness, which is just how bright a star appears to us here on Earth, depends on both its luminosity and its distance. There's this brilliant little relationship, brightness equals luminosity divided by 4 pi times distance squared. Because we know the true luminosity of our standard candle, and we can easily measure its apparent brightness from Earth, we just do the math to figure out its exact distance. To put that in perspective, if you have two identical stars, but one is 4 times further away, that further star is going to appear 16 times dimmer. This incredibly clever math allows us to step way beyond our own galaxy. Moving right along to Section 2, classifying the stars. Let's talk colors and temperatures. Now that we trust our cosmic measuring tape, let's actually look at the stars themselves. If you gaze up on a clear night, you might notice stars aren't just plain white. They have these subtle hues, and this brilliantly illustrates exactly how we categorize them. But look closely at this mapping. It is highly counterintuitive to how we usually think about hot and cold. I mean, on your bathroom sink, red is hot and blue is cold, right? Well, scratch that, because in astrophysics, it's completely flipped. A blue star is burning at a blistering 30,000 Kelvin, making it the absolute hottest class of star. Meanwhile, a red star is much cooler, sitting at around 3,000 Kelvin. Astronomers group these into specific spectral classes, from hottest to coolest. O, B, A, F, G, K, and M. A really fun way to remember this is the classic mnemonic, O, be a fine girl, or guy, kiss me. Our own sun, by the way, is a slightly yellowish G-class star. All these temperatures and luminosities are plotted on the Hertzsprung-Russell, or HR diagram, which is essentially the ultimate cheat sheet for mapping a star's life cycle. So, Section 3. The birth of a star. Let's look at the initial stages. We are officially shifting from our detective phase into our biography phase, because whether a star will eventually become a massive blue giant or a tiny red dwarf, the wild thing is that absolutely all stars begin their lives in the exact same way. Step 1 is the stellar nebula. This is a massive, cold, floating cloud of gas, mostly hydrogen and helium and dust, just floating there. But over time, gravity starts doing its thing, pulling these particles closer and closer together to form Step 2, a protostar. As it gets denser and denser, particles collide more frequently, and the temperature absolutely skyrockets. Finally, if that protostar gets hot enough, boom, we hit Step 3, the main sequence star. This is the magic moment where nuclear fusion ignites in the core. Hydrogen nuclei fuse together to form helium, releasing an enormous amount of energy. Remember Einstein's famous equation E equals mc squared?
Well, if a star converts just 2 kilograms of mass into energy, it releases 1.8 times 10 to the 17th power joules. That is a mind-boggling amount of energy pushing outward, perfectly balancing the inward crush of gravity.
All right, Section 4, Solar Mass Star Life, the steady worker. This is the life path for stars, roughly the same size as our own sun, the reliable, steady workers of the universe. They have a long, slow, and highly predictable journey. You can see the whole life cycle mapped out right here. We start with that stellar nebula condensing into a protostar, and then stabilizing into that yellow main sequence star we were just talking about. Our sun is currently in this very stable phase and is going to stay there for billions of years. But, eventually, the hydrogen fuel in the core begins to run out. When that inevitably happens, the core shrinks and heats up, causing the outer layers of the star to inflate dramatically. It expands, its surface actually cools down a bit, and it transforms into this massive, glowing red giant. So how does this steady worker finally exit the stage? Well, after the red giant phase, where helium fusion is causing all that massive expansion, the star eventually just sort of sheds its outer layers entirely. This ejected shell of gas is beautifully illuminated by the remaining core, creating what we call a planetary nebula. What's left behind in the center is step 3, a white dwarf. The star has completely collapsed into a small, incredibly hot, super dense remnant, and from there, it just faces a quiet, fading exit. The white dwarf emits less and less energy, slowly cooling down over eons until it's theorized to eventually become a dark, cold black dwarf. So, no massive Hollywood explosions here, just a really quiet retirement.
But what about the heavyweights? Section 5, the high mass finale, the rock star fates.
Yeah, not all stars go quietly into the night. Here, we pivot sharply to the totally contrasting fate of massive stars. These are the celestial rock stars, right? They live fast and they die incredibly explosively. Notice the big divergence in this evolutionary path compared to the last one. We start with the same stellar nebula, but because there's so much more material, we end up with a massive blue main sequence star. Because of its sheer crushing mass and gravity, it burns through its fuel at a completely blistering rate. When it runs out of hydrogen, it doesn't just become a regular red giant. Oh no, it expands outward to an unbelievable scale, becoming a monstrous red supergiant. But gravity is absolutely relentless. Once the fusion reactions inside that massive red supergiant can no longer hold up the colossal weight of the outer layers, the core simply collapses in a fraction of a second. This causes a massive rebound effect, a gigantic, violent explosion known as a supernova. This is literally one of the most energetic events in the entire universe. In fact, a supernova is so powerful that it's responsible for forging the heaviest elements in existence, like gold and uranium. It violently ejects these heavy elements, along with vast clouds of dust and gas, straight out into deep space. And beautifully enough, these newly enriched nebulae become the perfect nurseries for the next generation of stars and planets. So the dust settles. What is actually left behind after that spectacular explosion? Well, it depends entirely on just how massive the original star was. You're left with one of two terrifyingly extreme endpoints. The first option is a neutron star. This is a tremendously dense stellar core packed entirely with neutrons. It's so dense, in fact, that a single teaspoon of neutron star material would weigh billions of tons here on Earth. But if the original star was even more massive, like the absolute heaviest of the heavyweights, the core just continues to collapse under its own gravity until it forms a black hole. This is an unimaginably dense point in space where the gravitational pull is so intense that absolutely nothing, not even light itself, can escape it. Wow, it really puts our little corner of the cosmos into perspective, doesn't it? As we wrap up today's explainer, I want to leave you with this final thought. Our own sun is currently that stable worker, right? It's about halfway through its roughly 10 billion year main sequence phase. But in about 5 billion years, that hydrogen is going to run out, and the red giant phase will begin. It'll expand outward, likely swallowing the inner planets, very much including Earth. What will humanity do when that time comes? It's a pretty profound question when you look at a true galactic timeline. Thank you for learning with Lesson BCE. Keep exploring the universe and discovering the wonders of physics. Don't forget to subscribe and like our channel for more exciting lessons. See you next time!